Go to TAPgiles.com to learn dreams, engage my services, and support the channel.
Okay, next is the vector cross product, which is like the dot product, but like a step above. We're going to start with a vector again, and this one's just pointing wherever. All this stuff is 3D, it doesn't matter how they're pointing. First, what would be perpendicular, a perpendicular vector to this? So that would be perpendicular. We know if it's further around like that, it won't be perpendicular because it's more than 90 degrees. If it was pointing up like that, it would be less than perpendicular because it's less than 90 degrees. But there are other possibilities. So that would be perpendicular as well, because if you looked at it on this side, it's perpendicular. And if we rotate it more and looked at it from this side, this is also perpendicular. So actually it has all of these vectors that are valid perpendicular vectors to this first one. So you can imagine all these vectors pointing in all these ways in an infinite number. So we need to kind of narrow down which one we're actually going to use. Now I have a copy of that, and this one will be green. So we have this as another reference vector. So if this was like that, so you could put this vector we get out along that direction, because if you look between those two, it's got a right angle, and if you look between those two, it's got a right angle. Or you can put it over here, because if you look from this angle, and that's got a right angle, and between those two, it's got a right angle. So it could be either of those. And it kind of, if you think about these kind of circles where they intersect, they kind of make a line where it would make sense for that vector to be. So which one does it actually give you? It gives you one of those vectors. Spoiler alert. But which one does it choose to give you? It actually chooses based on the handedness of the engine. So Unity, another games engine, is left-handed, and Dreams is actually right-handed, and maths stuff tends to be right-handed for these cross products. But what does that mean? It's got a hand there, and we got some stuff in a chip, and we want to learn about the right-handed cross product. So if we take your hand at home and hold it up in front of you, and then do that, then your fingers will turn different colours. No, if that happens, see a medical professional. So your thumb sticks up, and then your first finger, your index finger, points, and then your third finger points like perpendicular to that, like pointing towards you. And you do that with your right hand, and that's why this is called the right hand rule. And that corresponds to the first bit that you wire into there, and then the second bit which you wire into there, and you get out the third bit out of here. As an aside, the right hand rule also applies to rotations. So that, which way a positive rotation will be. So if you have a rotator, if you point your thumb up where the stalk is, then you curl your fingers round, then that's the direction the positive rotation will be going. And if you set this to a negative rotation, then it's going in the opposite direction to the fingers. So everything in Dreams is right-handed. That's why they talk about this stuff being right-handed. So as we saw with our vectors, it's choosing this one. So the way you remember, and if we like rotate it, you can see it's matching the directions of this. So yeah, so if you give it the thumb and the index finger, you'll get your middle finger arrow direction pointing out. But the cool thing about this is these two, the reference ones, don't have to be perpendicular to each other. So even if you do like that, they'll still have, like this one will have infinite possibilities around there, This one will have infinite possibilities around there, but then you'll have, where they intersect, you'll have these arrows, and that's where you'll get your vector from. So if we look at like this, we got a perpendicular right angle there, and then if we look like this, we got a perpendicular angle there between the green one. So it's still perpendicular to those two. And in fact, what you can do then is you can forget this one, and you've got these two now, and then use this one and this one as the references. So then you'd use this one as the second one plugged in here as a second reference vector, and it would give you that one out. So you started off with that, where this one isn't perpendicular to anything, and then you get out three nicely perpendicular vectors. These aren't perpendicular. It will give you the vector pointing in that direction, but it won't be normalized. So it could have a smaller length. It might have a smaller length, but still pointing in the right direction. And then you can use the normalize vector operation to make it the right length again, and then use it for things. So that's another way of kind of figuring out the similarity between these two. Is as it's closer to that, it will give you a smaller output vector that's got a shorter length. The length of this vector is actually double the area of the triangle between these. So I'll move that out of the way. If you had a triangle going between those vectors, you can see how when they're like almost parallel, that triangle has very little area. And as you go over here, it gets more area, and then it gets less area again. So you know how normally you'd do that to get that, right, with the right-hand rule. As you start to not be doing that properly, so as this starts to go up here and then back over here, like the order should be red is going this way and then green is perpendicular over here. But as you're going over here, the length of this gets shorter. So while it's perpendicular, this is at 1. And then as it goes up here, this gets shorter and shorter, like that. And then as it goes too far, you're effectively putting these into the calculator in the wrong order. So this is actually going to be pointing in the wrong direction and giving you a negative length. Yeah, it will just be a vector pointing in the opposite direction, as if it had kind of negative length going along here. And then you keep going around and make it perpendicular again, and it gets longer like that. So you can get both sides of it if you want to, if you just like flip these around, or just as these change during your gameplay, then it can like point in different directions. And that's kind of another way of finding out how similar these are. And also the like direction, so like it's rotated left from the red one, or it's rotated right from the red one. So you're getting this point in a different direction. Oh yeah, so the normalized takes that, what you get out of the normal cross product, and then normalizes it. So then it becomes just one, a length of 1, and then it doesn't care like how long the vectors were that you plugged in. So if I put this reference thing into the vector cross product, so if we just quickly test this, and then we wire that into this one. Okay, cool. So it's rotating to, this one just rotates based on the vector it gets out of here. So if I now rotate that, it doesn't really care because that's still perpendicular. If you rotate it around that way, it's going to adjust to still be perpendicular to these two references. Yeah, and it still stays perpendicular to the reference ones going into here.
Thanks for watching. I hope you learned something interesting. Go to patreon.com/TAPgiles to learn something new every day.